start this lecture 23rd with a thought process. A family must have enough food for body, mind and soul to fuel the fire of life. If I look at today's family, it does not have that. So, let us recall what we learned in the last lecture. If you look at, we basically looked at one dimensional laminar premix flame, right, and then we invoked the equation of mass, momentum and species, and satisfying the conservation along with the energy, and they try to derive a relationship for laminar burning velocity. And if you look at why really we want to look at laminar burning velocity, of course, the flame is laminar, therefore, we need to look at laminar burning velocity. When the flame is turbulent, we need to look at turbulent burning velocity. In real situation, turbulent burning velocity will be more important than the laminar. Fortunately, the turbulent burning velocity can be related to laminar burning velocity. So, if you understand the laminar burning velocity or laminar flame, we can somehow manage to talk about the laminar turbulent burning velocity. Question arises, why burning velocity? Why not something else? For example, flame temperature, right? Why you are looking at burning velocity, spending a lot of time to derive a relationship? Because that is the only one parameter in case of premix flame, fortunately, which can characterize the entire flame. And this laminar burning velocity can be related to several other concepts like flame thickness, ignition energy, quenching diameter and several other blowout phenomena and then flashback. I do not know whether you are aware or not, but as we go along we will see. That means, we using a simple parameter burning velocity, we can really explain and understand a lot of phenomena associated with the flame, premix flame particularly, and also the diffusion flame to some extent, but in diffusion flame we define some other term, not the burning velocity, right. So, now let us look at flame thickness, right. If you look at flame thickness, and we have already divided the flame into 3 zones. What are those zones? Is a preheat zone, reaction zone and recombination zone, right, 3 zones. Question arises, when you talk about thickness of a flame, what you will say? Can we take all 3 zones, or we will take the reaction zone, or we will take the preheat zone, or we will take combination of some, right. There is a lot of debate about it, how thick is flame is, and we will be using an approximation also whenever I will be talking about diffusion flame and droplet known as thin flame approximation, right. And as I had mentioned earlier, flame is generally very thin, right, and naturally one has to take care of the reaction rate, right. But we will be using a what you call another way of looking at in terms of temperature, because in experiment one cannot really define where the peak reaction rate is occurring, right, and then talk about it, but of course, numerical people do use it. So, there are several definitions of flame thickness you will find in literature, but we will be restricting to one of them, and that is basically based on the temperature. For example, if I take a temperature over here, which profile I have shown T u, this is unburnt mixtures, and if I can assume this is along x direction, this is of course my temperature, and if I take this is from x starting from here and it is infinity, what you can see the temperature profile, you see the temperature is remaining constant. After that it is changing the slopes, and again like it is increasing and changing the slopes. So, when the slope is changing, right, there will be some inflection point, right. And what I will do, I will draw a parallel line here, and I will draw a parallel line here, right, and draw a tangent to this surface, and it will cut over here. So, that, and whenever it will cut this tangent, I will say this is nothing but my flame thickness, This is physically, right, but how we will do it mathematically? What do we are doing? We are basically saying the temperature difference divided by the temperature gradient at the inflection point. Slope will be changing, somewhere ignition will be occurring. So, there we call it as the inflection point, and then we do that. So, that means it is basically a flame thickness we can define mathematically, ratio of maximum temperature, that is T f, difference, and that means with respect to the unburnt temperature T f minus T u divided by dt by dx ignition, right. Ignition we are taking for our convenience, because we know this gradient from our analysis, right. Okay. Is that clear? So, we know that temperature gradient will be defined, but to talk about this temperature gradient, we have already approximated. See, if you look at this, is basically approximation is equal to 0.75 T A plus 0.25 T U, right. There is nothing very sacrosanct about it. Somebody can say, look, it is not 0.75, it is 0.7. It may be possible, right, and other was 0.3 U, right. It can be, but we are using this just to track this problem or make it tractable or handle this problem easily. The temperature gradient at the flame surface, we know that dt by dx, this we have already derived, is equal to 3 by 4 m dot double dash, keep in mind this is f and this is f, right. This is a bar average, right, Cp by kg T f minus T u. And what we have done, in place of T I z, we have used this terminology, okay, right. So, what we will do now, we will just substitute over here. If I substitute over here, what I am getting? I am getting T f minus T u, right, divided by 3 by 4 m dot triple dash f Cp, and kg will go here, and T f minus T u. So, this is cancel it out, right. So, what I will get then? I will get basically, right, delta L is equal to 4 by 3 kg, right, divided by Cp m dot f double dash bar. That means, this is the average reaction rate in the reaction zone, right, that we are considering. It is goes on changing, but we are taking, because we will be using Arrhenius equation for a global reaction, right, one for a single step chemistry, right. So, therefore, we can get that, and we know that m dot triple dash m dot is basically is rho u s l, right. We can find out that delta L is equal to 4 by 3 alpha by S L. What I will do? I will just put this thing, and like if I know this m dot f, I can substitute those values and arrive at 4 by 3 alpha by S L, right. And how it is, I am just leaving, you can look at it. That means, it is what he is saying, alpha is equal to kg by rho Cp, right. And what you can see from here, that means flame thickness, right, is a function of laminar burning velocity. As the laminar burning velocity is dependent on what? Inlet temperature, dependent on the fuel air ratio, dependent on the pressure, dependent on the type of what you call fuel oxidizer, right, system. So, naturally what I am expecting that flame length will be a function of inlet temperature, pressure, equivalence ratio and fuel and oxidizer system, right. That means, what you expect this one? If I say how this flame thickness will be varying with respect to equivalence ratio, that means I need to look at how it is varying, how the flame laminar burning velocity is varying with the equivalence ratio. You remember that the laminar burning velocity for a methane air system or for any hydrocarbon air system, right, this is my phi, phi is the basically equivalence ratio. How it will be? It will be something, if I take around 1 here, right, and this is lean side and this is reach side, what it will be? It will be something that means around 1.05 there will be peak values, right. Now, if I want to draw a how this flame length, how this flame thickness will be varying with respect to equivalence ratio. If you look at my burning velocity is very higher here. So, naturally this delta L is proportional to 1 by S L. So, I will get a minimum value, yes or no, right, because the burning velocity highest there. So, if I keep all the things are same, inlet temperature and all this pressure, all those things, then naturally it will be constant. You can say like other things maybe little bit changes will be, but it will be proportional to 1 over S L, right. Burning velocity is higher, that will minimum. So, if it is on the lean side, what it would be? If I draw delta L in this, what will be? My value will be somewhere very low values, and then other side it will be like that. This will be delta L, right? Yes or no? Because my burning velocity is dropping down both on the lean and the reach side. Of course, slope will be different, the rate at which it will be dropping down, but it will be just opposite that we will see how it is. So, let us having talked about this flame thickness, we will be looking at another very important aspect, that is the flame extinction, right. And if you look at why you need to study this flame extinction, because we know that fire or the flame is a very dangerous thing. We have seen that some of the houses gutted into fire. You might have seen nowadays lot of buildings even catching fire due to some what you call negligence on the part of there. But earlier days there was a lot of way of handling fire. Of course, if I remember earlier days in village, the whole village will be turned into ashes, because at that time thatched houses are being used, right. But question arises, fire is very important for our life. So, also but how to control it is also important, and what we do in all the engines like what you call rocket engines or the gas turbine engine or any other engines where we generate power or the thrust, we always try to control the fire or control the flame in it, right. I am using fire and flame in a interchangeable, keep in mind it is not supposed to, but I am just using for my just convenience sake. So, flame has to be contained inside combustor, that is important. Now, there are several safety issues are there. If you look at, there are several kind of safety issues which one can think of. That means, we must learn how to contain a flame, how to control a flame. One, of course, in laboratories like we always worry about whether how to douse a flame if it will occur accidentally. So, also in the homes, elevators, of course, some example in the big houses, and very important, the aircraft safety is very important, that is also being talked about. And you know, coal mines is another place where it is quite important. You may not be knowing, or some of you may be aware also, that we are having, you know, mine fire, coal mines fire, which is existing since 1916, and today it is also continuing, and we do not have any solution how to douse the fire, particularly in the, you know, in the Jharkhand region, Dhanbad region, you know, like there the fire is engulfing large amount of coal, million tons of the coals, you know, are being burnt into ashes. We do not have a solution, right. So, similarly, it is very important. If you remember that, you know, in order to contain, you know, like avoid the flame in the mines, a person had invented a lamp. Do you remember who is that person? And then, you know, he is basically Humphrey Davy, right. And there is of course, nuclear plant where the, you know, fire is a very important one and has to be contained. So, also the spacecraft. Now, question arises how we can extinguish a flame, how we can extinguish a flame or a fire. I am using it interchangeably, right. What are the ways? We have seen, like, you know, candle flame, whenever the light will come and whenever light, what you call electricity will go away, we generally use candle flame for temporary, right. Of course, nowadays emergency systems are there, light system with battery, but we always how do you extinguish a candle flame? Just blow air. What we are doing by blowing air, right. What really we are doing? How it is being doused or extinguished? And whenever the fire, you remember, like I do not know whether you people are involved in extinguishing a fire or not, because nowadays all are self-centered. Earlier days, whenever fire is there, we will go with the people and let us, you know, help them. Today, the, you know, in cities and others, even in village, people are not cooperating, right, because people are more selfish nowadays. Anyway, let me get into that. What really we do? We just go and pour water, you know, like bucket of water we used to take in the village, and today of course, you are having a hose pipe which will go and put water. So, water also we can douse. If sometimes, you know, something happens, we spray water, right. Is a benign, water is not there, what could have happened, right. So, now question arises, what really is happening inside? And sometimes you might be knowing that is a fire extinguisher, sometimes carbon dioxide gas or some, you know, kind of a nitrogen we use. What really happens? Is it really something happening like some heat being, you know, how this flame being propagated? Because of heat being generated, and it try to consume and prepare the things and go, right. Now, of course, like what you call, when we do that, means is a one way thinking of using the heat. You know, if I manage the heat being generated due to the flame, rather I cannot make it self sustained. So, flame will not be there, right. That is the one way of doing it. Another way of looking at, you have seen the kinetics plays a very important role. If temperature is higher, then only the reaction will be taking place. If temperature is low, can really reaction take place even though fuel air there. For example, if this room is mixed with fuel air ratio, which can be burnt, but if there is no ignition, if there is no heat sources, you cannot really this thing. If a temperature is very low, I know, then nothing will happen, it will be there. Maybe it will affect your health because of fuel air there, but it will not really be converted into a flame. So, if you look at all these extinction process can be divided broadly into two categories. One is thermal effect, right. That means, what we use is that one example is water we use, that will be spray, and then, you know, it will be small droplets, surface area will increase, evaporation will go on, you know, like evaporation will be enhanced, and then there will be also addition of diluents, you know, there is a heat transfer and also diluent. And there is another way of that, alteration of kinetics. For example, I will use halogens or some other gases, right, which will be altering or inhibiting the reaction to take place, right. I can put some other gases which will be accelerating or enhancing the combustion by changing the kinetics. So, combination of both can be used, to talk about basically what you call flame extinction. What really is happening, we are trying to quench the flame, right. For example, we quench the mob as well whenever they will go to what you call violent. There is a very interesting way of quenching the agitation or the violent. In recent days, a lot of things are happening because of no reason, very kind of things. So, how to do that? This is again, you will have to quench. You will have to quench the aspiration or the what you call violent mind of a person. Similarly, the flame is considered as a violent, right. So, you need to quench it. What is the way of quenching it? As I told, it is the energy which will be released that you will have to contain, right. That is the basic principle. Either you do by thermal effect or do you do by the kinetics, it is the energy which is matter altogether, right. So, similarly, when people, if you look at the youngsters are becoming violent nowadays across the globe, in India is no exception. How to handle them is a very important aspect. That is why I gave a quote like, you need to look at other aspect of life. So, coming back to that, that means we will allow the flame, how we will talk about this quenching our flame. One way of transferring the heat, if the flame is there, how we will do? You will have to put a water or something. Suppose there is a tube where the mixtures are there, right, particularly in case of premixed flame. Then what you will have to do? You will have to transfer the heat. How we can do that? You can say I will cool it. You can mix, or without mixing you can do that. That means, we can allow the flame to pass through a narrow passage, right. Then what happens? It will be quenched or it will be accelerated. If there is a mixtures, for example, I am taking a passage, like a tube. This is the tube where this is a fuel air mixture, air mixture, right. And there is another tube which is very, very small. If you keep in mind that this is D, very big diameter, this is a very small diameter. This is also mixed with the same, fuel air. If I say this is methane plus air and this is also methane plus air, both are the same and same equivalence ratio. I can say, let us say phi is equal to 1. For example, okay, both are same, and I will ignite here, right. This is the ignition source or a spark I am creating. Similarly, I am creating fire. What will happen? This is, let us say, like a 5 centimeter or maybe 7 centimeter. This is a, or let us say this is a 10 centimeter and this is 1 mm. Right, I will say this is 10 centimeter, this is 1 mm, 1 order of magnitude difference. What will happen? Is it flame will propagate in this? See, if I will do it, same amount of ignition energy I am giving, same fuel air mixture, what will happen flame? Will it propagate? And keep in mind that there is a lot of heat transfer is taking place here. That means, is going out, heat transfer, right. This is going out, right. Similarly, this is also going out. What will happen in the smaller diameter? Will it flame will go? If I make it small, if it is going at 1 mm, if I will make it 0.5 mm, will it go really? If it is, I will make it 0.2 mm or 0.1 mm, I can take another tube 0.1 mm. Right, the same thing, mixture CH4A phi 1, this is 0.1 mm. So, you will find that what is happening to the heat loss, there is a two things, one is heat being generated, because the same full air mixture you are giving ignition energy, let us say some right, and in another heat loss. Heat loss can be several things, right, it can be conduction, it can be convection, it can be radiation, right. Let us say total heat loss whatever is happening. So, heat loss, how heat loss is changes along with this, that means heat losses, if I look at losses, heat loss is changing. How it is changing? Is it the same heat loss is happening for the all diameter what I have taken? What is happening? Heat loss is decreasing as I going, like it will decrease like this, or it will remain same, or it will increase. There might be three things, right. One is heat loss will increase from here to there, and another heat loss from three cases will be decreasing, right. That means, here it is increasing, here it is decreasing, right, or it will remain same, it will not change between three cases, three diameters, right, what I have considered. What will be happening? Heat loss will increase as you go along with this, that means, less heat losses from here, more heat loss from here, and most heat loss are the largest here, smaller, right, because the surface area is being increases as compared to the volume of as compared to the volume of fuel air mixture being burned, that is very important, right. So, therefore, and this concept was recognized by Humphrey-Davy long time back, and who employed in a mine, who employed in devising a mine safety lamp. Did you observe this thing in your experiment in +2 science? Suppose there is a premix flame, right, there is a premix flame. This is fuel plus air mixture, keep in mind this is like a Bunsen burner, right. This is a flame. If I put a net, over here, net, what is this net? This is a stainless steel net, very fine mesh, or you can call net or a mesh, mesh is a better word, right, stainless steel mesh. What will happen to the flame? If flame is there, I put like this cross, what will happen? Spread. What will happen? In the bottom there will be also flame, and the top there will be also flame, right, is not it? What you have observed? What did you observe? There won't be any flame here, right, flame will be, and as you move this mesh, you can take flame with you, of course, to some extent, right. Flame will be dangling, depend if you dance, you can make the flame to dance by with the help of a mesh, and this concept was used by the Humphrey-Davy to contain the flame. Why it is so? That is because he will be handling with the quenching, he will be trying to quench the flame. Flame cannot propagate through the pore holes of the mesh, and then we need to look at what is flame quenching, right. So, that is a very important concept. So, what is flame quenching? As I told you that whenever heat loss is higher as compared to heat being generated, there will be flame quenching, right, or equal to, right. That means, for a flame to propagate, energy released due to chemical reaction must maintain high temperature, otherwise it cannot. If it is there, is all the heat being generated is going away due to heat loss, then natural temperature cannot pick up. So, you cannot have, right. And heat loss can be increased by decrease the passageway, resulting in low reaction rate. As I told you, surface area will be increasing when you decrease the diameter or the width of the two channel, right, as compared to the volume amount of heat being generated in a specific volume or particular volume. So, energy release rate reduces, temperature drops below the self ignition temperature, as a result there will not be any quenching, and that leads to the flame quenching. If you look at the whole process involving what is basically the heat balance, right. So, now what is the quenching diameter? As I told you, I will conduct experiment, right, in this way. I will take some diameter d and see whether flame is traveling or not, right, and I will take the same mixture, go to a smaller diameter, I will go to smaller and find out at which diameter flame is not propagating or not going through the thing, and that is known as quenching diameter. This is a critical diameter of a circular tube below which flame cannot propagate, right. And people have conducted experiment also for channel. It is a tube, right. This is a channel, two plates they can take and conduct experiment, that is also known as flame quenching width or the thick width kind of thing, right. So, some of the data you can look at it, methane air, right. If you look at it is having 2.5 mm quenching diameter, but if I use oxygen, methane and oxygen, you will see it has been reduced 0.3. And similarly, for propane air, acetylene air, if you look at the quenching diameter is 0.8 as compared to methane air. Why it is so? Because the burning velocity is higher, that is 140, whereas here is 20. If you look at hydrogen air, the burning velocity and for stoichiometric mixture, whatever the data I have given burning velocity for the stoichiometric equivalence ratio equal to 1. So, it is very higher and it is also smaller, and whenever oxygen you put, so naturally it will be smaller. So, we need to now relate this quenching diameter to the laminar burning velocity. We will do that, and using a very simplified analysis. What I am doing? This is basically a tube, this is a tube, what you call this is a tube having diameter of dq. I am saying this is the quenching diameter, right, and this is the flame which is traveling through that with a velocity, burning velocity, that is SL, and the delta L is the thickness of the flame, right. That means thickness in which all heat being released or all the things are being, and some conduction is going on. And here we are considering that there is no heat loss due to radiation, right, and also convection we are not considering, right. What we are doing, whatever the heat being released is basically going away due to conduction. This is an approximation, keep in mind, and we will be doing some more simplification. That means, for this condition the flame can propagate only if the heat release or heat generated due to chemical reaction is greater than the heat loss due to heat transfer. In this example or in this analysis, we are talking about only heat conduction, right, but in complex analysis you need to talk about the radiation as well, right. But now, that means it will be quenched whenever the heat generated is equal to the heat loss due to conduction. So, let us look at rate of heat generated per unit volume. That will be what? In this volume it will be Q dot triple dash will be m dot f delta SC, right, heat of combustion. This is being consumed and this is being released. So, this is the amount of heat. Of course, keep in mind that here we are assuming all the fuel is being burned and releasing it. In a real situation, it will not be. This is an idealization. Okay. So, heat generated in the volume will be basically in this volume, this is per unit volume, this is per volume will be what? This term into pi by 4 d q square. This is the like a cross sectional area. If you look at this will be like this, right, and this is your what you call delta L, and this diameter is basically dq. So, is a cylindrical kind of thing. So, 4 by pi by 4 d square and del L. So, heat being lost due to the wall conduction, right, will be what? Conduction is kg pi dq, this is the surface area, pi dq, and delta L is your surface, and dt by dr. Is the temperature, we are saying only the temperature gradient along the r direction, the temperature gradient along the z direction is negligibly small, but in real situation it is not, right. We are assuming, because the gradient along is much higher as compared to the gradient along the z direction. That is one assumption. And if you look at, I want to estimate this dt by dr. For that, you need to solve, conjugate, or you will have to handle the conjugate heat transfer, because the solid, this is a gas will be here, right, and this is solid. So, you will have to take care of conjugate heat transfer is quite complex. So, what we will be doing, we will be simplifying it, and what we will be doing, if you look at this temperature profile higher here, and this is a not a linear, right, it cannot be linear, it will be going and then also increasing, and then after certain distance it will be almost constant, asymptotically it will be decreasing, right. But what we are assuming, we are taking a what you call linear temperature distribution, like we are saying that this is like that, and we are also assuming there is another assumption, we will saying this is a uniform temperature in the gas, but here it is linear, it will be like this kind of thing, linear, right, it is not asymptotically decreasing. So, therefore, we can say that dt by dr is nothing but Tf minus Tu, because we are assuming this thing, and dq by C. In principle, C can be equal to 2 if you look at roughly, but we can make it more accurate by considering C as a constant, which can be greater than 2, because if you look at it, right, in linear if I take it can be 2 kind of thing and do manage that, but we are not, right. So, quenching diameter, if I put this thing here, substitute these values here, and then I can say that Q by heat release is equal to Q conduction, right, and I will get that, what I will get, if I look at this, I can write down as kg pi dq delta L Tf minus Tu dq by C is equal to m dot triple dash F delta Sc pi by 4 dq square delta L. So, this will cancel it out, right, and this dq I will be cancelling out here, pi will cancel it out, and I will get the dq, because dq square is there, right, in this right hand side. So, dq will be nothing but 4 C, this is my 4 will go this side, right, and there is a also C will go here. So, 4 C, C is a constant which can be varied, will be greater than 2 always, kg Tf minus Tu divided by delta Sc m dot F triple dash, right. And you know that delta Sc is what? If you remember that delta Sc approximated as nu plus 1 Cp Tf minus Tu. This is an approximation, right. So, we can use that, and 1 over m dot F we can express as what? As a burning velocity. You can look at those expressions, and if when you do that, what I will do, I will after simplification I will get dq is equal to root over 8 C and delta L. Once I get laminar burning velocity, this I can put in terms of flame thickness. So, if you look at this dq is basically proportional to the flame thickness, and it is a constant. That means, dq will be higher than the flame thickness, right. So, of course, quenching diameter table we have seen. I am not going to talk about that, but let us see that how it is varying, right. And keep in mind that delta L is proportional to the what you call burning velocity, because it can be related 4 by 3 alpha by S L. That means, the dq will be also function of, or quenching diameter is a function of what? Equivalence ratio. It can be function of inlet temperature, it can be dependent on the pressure, it can be dependent on the type of fuel oxidizer system, right. So, let us look at how it is varying. This I have shown you flame thickness, and these are methane air premix flame system, flame thickness versus equivalence ratio. And this plot is basically quenching distance in mm, right, and this is flame thickness on the mm. If you look at, it is around 1 or 1 point, this is a very minimum values, and similarly here also is having, but it is little shifted to that. That means, around 1 it is having lower values, and this is having what you call higher values than that of the quenching distance. That means, quenching distance is having higher value than that of the flame thickness, right. And nature is almost similar, but only thing in the reach side it is little closer to that, because you are having multiplying, and there might be some kinetics involved in that. So, what I am saying, by using a very simple analysis, right, which is quite simple, what we have done, we can show the trend, and trend is quite good. I mean, it can give you the overall feature, and it can replicate. These are all experimental data, it is replicating the trend, okay. And you can use also for as a design tool for that. So, limit mixtures, if you look at, we will be talking about another concept known as flammability limit mixtures. That means, there is a flame can propagate only when within the range of fuel and oxidizer ratio, right, and it cannot propagate beyond certain limit, right, both in the lean and reach limit. And but question arises how to determine the flammability limit, and this is very important from the safety point of view as well. And also, you should not go on claiming or trying it out to burn some mixture which it cannot be, right. And this again will be related to what? This flammability limit is related to what? That we will see. So, there is several ways of doing it, but the most important or which is being used is a vertical glass tube, particularly for atmospheric pressure condition, which is length is 1.2 meter length and 50 mm ID inner diameters. And why not a smaller diameter? Why not a big diameter? Why 50 alone, right? So, if you look at typical experimental setup, will be looking like this is a tube, and it will be filled with the fuel air mixtures or fuel oxidizer mixture. Air is of course one of the oxidizer, and then you ignite in the bottom and let this flame propagate and see that how far it is moving, right. Generally, it should move half of the length, that is 1.2 meter as per the standard of American standard, like American petroleum standard kind of thing they use. It should move half of the thing, right. Suppose then only you can say it is flammable. Otherwise, if it is moving initiated, but is not moving half of the portion, then we call it as a inflammable or like not flammable, right. So, that is a limit. It can have both what you call lean limit. If you look at here, the burning velocity I have shown with the fuel air mixture, there will be limit beyond which flame cannot move. That means, flame will not be having a what you call any tangible burning velocity, right, because it will not really move. Now, question arises like like it is having a why it is happening both the lean and reach, why it is flame is getting quenched. Basically, flame is getting quenched, is not it? Why? Because I have already told you, and when I am saying the word flame is getting quenched, that means heat loss is there, and then it is just getting doused and not propagating. That is the one aspect, and other aspect what you call you can see from this that flammability limits changes from a certain range in which it will working as you are increasing the temperature, right, because burning velocity dependent on temperature and SL also is increases. So, you will find the limit mixtures are also enhancing, that means it is become broader when you increase the temperature. And keep in mind that I had asked you the question why 50 mm, because if I use a smaller diameter, then the then what will happen, it will be affected by the heat loss, then whatever mixture you will get, the limit mixture won't be right. But if I use a bigger one, you can say I can go for 50, then it will be little hazardous to handle. So, therefore, 50 people have found out this thing. There is another way of that, when the flame is propagating from top to the bottom of the tube in a vertical, this is a vertical tube. So, what is happening? The flame is affected by the hot gases, these hot gases will be here, it will be trying to push the flame. As a result, you will get a different mixture. If I ignite over here, that means flame will be propagating downwards, right. What will happen? My limit data won't be, or the flame burning velocities or the flame propagation won't be affected by the hot gases or a buoyancy, natural convection, right. So, therefore, the people always prefer the downward propagation of the flame for making the flammability limit. In other words, the flammability limits obtained by the upward propagation and downward propagation will be different, right. That you can keep in mind, and that is due to, as I told you, flammability limit is determined upward propagation flame from the ignition source. Mixture is said to be flammable only when travels above the half of the tube. Larger diameter preferred as it provides consistent result and free from the quenching. This is very important. Like, and as I told you, direction of flame propagation affects the flammability limit. Flammability limit varies linearly with temperature. So, it is as I told, it is dependent on temperature, it is also dependent on the pressure limits. If you look at pressure, I have shown this equivalent reason. These are flammable mixtures here inside here, but here outside it is non flammable, right. So, you can see that lean side it is having a kind of things, whereas the leach, if I look at this pressure, right, here it is slope is little shallow, it is a little steeper here. So, of course, so pressure has a significant effect in flammability limit, lean side is not affected significantly by the pressure, right, whereas the reach limit becomes wider because it is like if I go on doing that, I will be not changing. Suppose I will go to another pressure, whereas here if I go over here, there is a lot of more change, this change is higher. So, that means reach limit is becomes much wider, right, than the lean side. And let us look at the some data which I have taken. Methane air stoichiometric is 9.5 and lower flammability limit, that is this side lean side, or you can say lean flammability limit, but generally lower flammability people talk about it 5%, upper flammability is 15%. What you can see is that is a similar trend you can see for ethane air, that is 5.6 and 2.8, 12.4%, and propane air you can look at 5.6 stoichiometry and LFL 2.1, 9.1. If you look at these data, can you observe something from these data for all hydrocarbon what I have shown? Can you look at data and tell me what do you observe? Some trend can you get out of this? If you observe that the lower flammability limit is almost the half of the stoichiometric fuel, isn't it? Roughly, if 9.5 it is 4.75 kind of thing. So, it is actually approximately 5, 5.6, 2.8 similarly, whereas the reach limit is not really related. Of course, when you go for CO where is having a very wide flammability limit, but if you go for hydrogen air, the flammability limit is quite wide as compared to hydrocarbon, 4% of fuel and 74.2% of fuel under atmospheric condition, right. This is whatever data I have given under atmosphere. So, therefore, whenever you are handling hydrogen, one has to worry about it because it is having a wider range of flammability from the safety point of view. So, there is another concept which I will be trying to look at today, that is the ignition. What do you mean by ignition? Ignition is the rate of heat liberation near the ignition zone, right, must be greater than the heat lost by the conduction. That means, if I am giving some amount of ignition energy, right, and whatever heat being it is going away at loss, then naturally my mixture cannot really reach a self ignition temperature to have a combustion, right. So, therefore, one cannot have ignition at all, maybe fuel air mixture they are within the flammability limit, but I cannot have. That means, what will the minimum ignition energy one can think of? One can think of the energy generated in the flame, like that means the ignition energy must be equal to the whatever the heat loss or greater than heat loss by conduction. So, now what we will do? We will have to look at energy generated in the flame is equal to what? Sensible enthalpy into mass of it, and for that what we will do? We will use the same idea what we use for discussing about quenching diameter. We look at in between this diameter the flame is there and which is traveling and having a thickness of delta L, and it is the dq. Of course, I need to have a ignition energy beyond the quenching distance, right. If I will give more than that, then my flame will be can propagate, I can initiate ignition, right. So, let us look at, we will be doing again some heat balance, how much heat being generated, how much heat being going away, so that I can have a sustained flame for the ignition to occur. So, if you look at energy generated in the flame will be basically sensible enthalpy, this Cp Tf minus Tu, because I am assuming this is the Tf and the mixture which is coming basically Tu, like if flame is traveling here, the mixture will be here which is under the Tu, right. So, Tf minus Tu Cp pi by 4 dq square, this is the into the delta L. As I told, this will be like a cylinder I am considering. So, pi by 4 dq and into L, this is nothing but your delta L, right, and this is your dq. So, that volume how much it is into the density rho is there, rho into volume, it will give a mass, and this amount of energy is nothing but your minimum ignition. This will has to be given, so that it can attain the flame temperature. Once it attain flame temperature, it will propagate, there is nothing more, right. So, that is the minimum ignition energy. So, substituting the quenching diameter, I can talk about this, substituting this value in the quenching diameter, I can get 2 pi c rho u Cp Tf minus Tu delta Lq, right, because this dq I can use the whatever I have used for this dq is nothing but root over 8 c d delta L, right. dq is equal to root over 8 c delta L, that we have already will put that values, and we know that delta L is nothing but 4 by 3 alpha SL. So, you will get M I when you substitute these values alpha by SL Q, Tf minus Tu and Kg. So, if you look at dependent on pressure, if I look at this expression, I will find that alpha is nothing but Kg by rho u Cp, and Kg and Cp you can say it is not changing with respect to pressure, but however, rho u will be changing. So, M I will be proportional to rho u square SL Q and pressure 3 n by 2 minus 1, right. So, because we have seen that SL is like n is the order of reaction. So, if you find out that minimum ignition energy is dependent on the pressure, so you can look at some of the things here, the minimum ignition energy, methane air, these are all for stoichiometric mixtures, you can see some number, it is in order of millijoules, right, and these are from the calculation one can get. So, let us now little bit dwell on how it is dependent on the pressure. So, we have already seen that it is if order of reaction is 2, what is happening here? It will be something 3 minus 1, it will be 2 kind of thing, right. So, if you look at the, if order of reaction is 2, minimum is proportional to minus P 2, is a very strong, dependent on the pressure. So, if you look at, if I plot this minimum ignition energy and plot here with respect to pressure, you will find that if around 100 atmosphere pressure, kind of thing, some amount of energy is having, but if the pressure decreases, right, what happens, that amount of ignition energy is very, very high. But if, of course, if it is, because it is going asymptotically, or going vertical, the slope is very high, right. And of course, here if it is the higher pressure, if I go from 100 to the 200, there is not much difference, if you look at this difference is very, very small, right, kind of thing. So, what is a, can you use the same ignition energy for flow conditions, and that is a one questions, but before that I want to ask you, we will be facing a lot of problem in the gas turbine engine, particularly at the higher altitude where pressure is low. So, can you use this same ignition? Certainly no. For the flow condition, we need to use 50 to 100 times that of ignition energy in quiescent atmosphere, because what happened, like there is a flow condition, heat losses will be there by convection, which you have not considered, and quiescent atmosphere you do not consider, right. So, generally for a typical gas turbine combustor, ignition energy 1 to 2 joule is prescribed for successful initiation combustion, even under the adverse situation. So, if you look at, we will be looking at some of the things when we discuss about gas turbine combustors kind of thing. Okay, fine.